So hello everyone, today we'll be discussing the AtCoder third question from the next DP contest. So unfortunately I have already made some submissions on this question. I was recording as usual and due to some glitch the recording got stopped. I didn't notice it and I kept going and made the submissions with normal DP approach and also the space optimization. So I'll try to explain it well. So let's get started. You're given three strings. S1, S2, S3, each consisting of lowercase English letters. Find the number of strings T of length n, also consisting of lowercase English letters, such that none of the strings S1, S2, S3 appear as a subsequence of T. Output the answer modulo 99824 something. Okay. So the question says you will be given S1, S2, S3. You will be given S1, S2, S3. You are supposed to make a string T of size n such that S1 is not a subsequence of T, S2 is not a subsequence of T, S3 is also not a subsequence of T. Alright, so this is what you are supposed to do. And the constraints are pretty basic. N doesn't exceed 1000, S1, S2, S3 doesn't exceed 10. So, how to solve this problem? We already know dynamic programming is an optimization on complete search. So, you should maintain a state. To this state, you would be checking by appending every character. Let's say you appended A. Let's say you appended B. Let's say you appended C. Let's say you appended D. So on. Let's say you appended Z. If on appending A, it results in an invalid state, prune it. If on appending D, it results in an invalid state, prune it. If on appending B, it gives you a valid, then you would be moving to the next state. So this particular state should consist of, since I say the word, you are moving to the next state. Some variable in this particular state should represent the current state you are in. So there's a variable, let's say n. You're moving to the state n plus 1. In n plus 1, once again, you already have B with you. You already have C with you. To this B, you can make it BA. You can make it BB. You can make it BC. You can make it BD. So until you can make it BZ. Right. When you do this, let's say some got pruned, one resulted in a good state. Okay, so now once again you are at position n plus 2 and n plus 2 is fairly the last position. Let's take n equal to 3. So place something here. This would be the last position. Fine. Let's say you once again place a few stuffs here and it resulted in the right thing. So one thing is clear, whatever the state you write, it should consist of the current state you are in, which is n. It should consist of n, the current level, the current stage, current configuration. It should denote n. And your pruning, what's the logic behind pruning? What is the logic behind pruning? You are checking if this A, let's say S1 is A, you cannot take A, right? You cannot take A as your first character. If S1 is A, you cannot take A as your first character. Fine, you cannot take A as your first character. So somehow you should match this with S1, S2 and S3. You should match the character which you're taking with S1, S2 and S3. So there's an interesting state idea which you can get from solving the problems LCS, LIS, etc. The string based problems is that in these problems, you never maintain the actual string. You always maintain the string length. So if I somehow maintain the prefix length of matched sequence of S1, that means if I maintain some P1, if I maintain some P2, if I maintain some P3, P1 denotes how much part of S1 you already have in your configuration of T. How much part of S2 do you already have in your configuration of T? How much part of S3 do you have in your configuration of T? This is what P1, P2, P3 denote. This is what P1, P2, P3 denote. So this is how the DP state would look like. So let's quickly make a DP table. For simplicity, let us take it as ABC. So the DP table would be how many dimensions would it contain? It would contain 4 dimensions. Okay, int got closed, vector got closed, vector got closed. One more. Fine. DP. Actually, I could have used something better. Let me show you. V. Yeah. So this is an extension called Fast Olympic Coding. A dot size plus 1. Vector int. And B dot size plus 1. Vector int. C dot size plus 1. Vector int. No, wait, this should be A dot size, this should be B dot size, this should be n plus 1, this should be n plus 1, sorry, my bad, n plus 1, because n is denoting that configuration, right? So instead of n, let's take it as I, because n is already the size. Let's take them as x, y, z. I hope you understand this much. And I know that extreme beginners are not watching my videos, so it's fine. Comma 0. So this is it. We have made a DP array. Fine. Now we need to iterate over I less than n, I plus plus, x equal to 0, x less than a dot size, x plus plus, y equal to 0, y less than b dot size, y plus plus, z less than c dot size, z plus plus. Now you need to write the transition logic. What was the transition which we had discussed? You would try out each character with it. So first thing, if dp of I, x, y, z is 0, there's no way you can do a transition from it. It should initially consist of one way. What does that mean? Empty string is a valid way, right? So if you're starting from what do you say? The parent of the transition is a state that's giving 0. That means it's a pruned state. We are not interested in the ones which have zeros. dp of 0 0 is equal to 1. Fine. So dp of I, x, y, z, if it's equal to 0, then you should just continue from here. Then try out all the characters for char ch equal to a to ch less than or equal to z. Try out all the characters and let's say okay, so now you need the prefix lengths. Now you need the prefix length. So let's say there's a length mu x. See, x is already the prefix length of which state? The previous state. The previous state or the current state, I would say. So the next x would be x itself. Okay, and the next y would be y itself. Next z would be z itself. Until we compute it, it would remain this. If a of x is equal to the character which you have appended, if a of x is the character which you have appended, mu x plus plus, if b of y is the character which you have appended, then mu y plus plus, because this indicates match. The current character which you have appended matches with the character, the next character of a. See, let me explain this. If let's say there's some a, b, c, d, if till here everything is matched, x equal to 3, right? X equal to 3. 3 is also the next index. 3 is also the next index. So if I check S1 of x, that means after whatever the part is matched, the next index, if it matches with the current character which I'm appending, that means till here everything is matched. Till here everything is matched. Is that clear? Let me explain it once again. You have A, B, C. Till here it's matched. X equal to 3. If I'm checking for D, S1 of X, 3 is also this index. This is also 3, 0, 1, 2, 3. Because of zero-based indexing, we get this good thing that the prefix length is equal to the next index. So when S1 of X happens to be equal to the character which you are appending, to T, let's say T is some A, X, X, B, X, X, C, X, X, and the character which you are appending is D. If D matches with D, then the length till here the match is formed. So mu x is equal to x plus 1, mu x plus plus, mu x plus plus. So this is what happens. This indicates match. And similarly, if C of Z is equal to CH, mu Z plus plus. And now let's try the pruning case. When do you prune it? If mu x equal to a dot size, that means complete A is a subsequence. This shouldn't happen. If mu y is equal to B dot size, this also shouldn't happen. If mu z equal to C dot size, this also shouldn't happen. In this case, prune it. Otherwise, let me explain you something. How do you calculate the number of ways? You would understand it if you dry run this code. Wait. Let's say t equal to 3, s1 equal to a, s2 equal to b, s3 equal to c. If this is the thing, alright, if this is the thing, and you have to calculate t equal to 3 blanks. Initially chance is 1. Okay, if you place A, you are getting nothing. Place B, nothing. Place C, nothing. You place D, you are getting one possibility. And you're moving to next level, f of n plus 1. And so far nothing has matched. N plus 1. You're moving to the next one. You're moving to this blank now. Okay? And so this is currently 1. When you place an E, you are once again moving to the next blank. Does E match with A? No. Does E match with B? No. Does E match with C? No. Then either you could have a D or either you could have an E. So you have two possibilities for this blank. When you try all the possibilities, at the end you would get 26 minus 3 possibilities, which is nothing but 23 possibilities. So there are 23 possibilities of placing a character here, which you would get at f of n plus 1, 0, 0, 0. Okay? We are getting this simple thing because we have taken all the characters as 1, 1, 1. The size is 1, 1, 1. The moment one of them becomes 1, it gets invalid. So that's how it works. So now we have f of n plus 1 calculated. Now it's time to calculate what can be placed here. If you place an A, it's a problem. If you place an B, it's a problem. If you place a C, it's a problem. You can place a D. You can place a D. That means you are computing DA, DB, DC. That means to the you're basically adding previous state to the next state. Let me explain. You are basically adding. Now you are at, after placing D, you are at n plus 2. D doesn't match with A, D doesn't match with B, D doesn't match with C. Okay? But you can have DD, you can have ED, you can have FD, so until you can have ZD. So that means you should be adding plus equal to f of n plus 1 0 0 0 0, the previous state. You should be adding the previous state, because when you pick one character, if you pick one character D, you can combine it with all the previous 23 characters. So that's how it works. So if it's not a thing to prune, what are you doing? dp of I plus 1 new x new y new z is equal to dp of I plus 1 new x new y new z plus dp of I x y z, and we need to perform a modulo. Fine. So that's how the transition is. Once you're done with the transition, the final results you would have would be at, let's say, take some variable answer, I equal to 0, I less than, let's take x equal to 0 because it's more intuitive now, x less than a dot size, x plus plus, y equal to 0, y less than b dot size, y plus plus, z equal to 0, z less than c dot size, z plus plus, answer equal to answer plus the last row, which is dp of n x y z, and we need to perform a modulo. Sorry, not return statement. Cout answer end L. So this is something that would work. So if I do run the test cases, all of them passed. Okay. Now, can we somehow space optimize this? So the answer is yes, we can. We can space optimize this. How to know whether you can space optimize a DP problem or not? Once you write the simple transition logic, observe that dp of I something is leading to dp of I plus 1 only. Okay, dp of I is leading to dp of I plus 1 only. So you need to maintain just the next row. You just need to maintain the next row. You need not maintain a whole new dimension for this. A whole new dimension for this is of no use, and it's taking at most 1000 space, right? So it's 1000 into 11 into 11, or 1000 into 10 into 10 into 10. So it's 1000 into 1000, which is unnecessary. You can eliminate this particular thing. By taking only the next row. You only need the next row, right? Why do you want to store the whole dimension for it? So I just need the next row, which I would write this as next dp next DP of, I'm completely omitting this dimension, nx, ny, nz is equal to next DP of nx, ny, nz. Wherever there's a DP of I plus 1, just replace it with next DP, the name next DP is equal to DP of x, y, z. Fine, DP of x, y, z. Same modulo. Now, the next DP would become the current DP for the next one. It would become the current DP for the next one. So current DP is DP. We need to make it next DP. DP equal to next DP. Fine. So this dimension is not needed anymore. Okay. And we haven't declared the next DP thing. Let's comment this first. Now we need a 3D DP. A 3D DP of a dot size plus 1, comma, b dot size plus 1, comma, c dot size plus 1, initially zeros. And the same thing we'll be declaring here also. We need a fresh next DP every time, so it should get created. Let's name it DP first. This should be next DP. We haven't placed a semicolon here. And you can completely eliminate this one. Yeah, no need of this dimension. And if I run this once again, okay, wait, we forgot to remove I here. Yeah, so everything passed. So this is how we space optimize the DP. So I hope the session was clear. Yeah, done, accepted. So thank you everyone.